Right, hello. This is ACT worksheet 203 exponents. And as far as exponents or indices go on the ACT out of 60 problems, about 4 will require knowledge of how to multiply, divide, distribute across uh, exponents or indices. And out of those 4 problems, one, about 50% of the time, we'll have to do a scientific notation. So what we'll do in this video is we'll look at some of the foundational rules that you'll need to know for the test with indices or exponents. We'll look at some of the most common pitfalls or mistakes that people make that the test tends to pick on. And we'll also look at scientific notation. And then after that, we'll try 3 problems from previous tests that have given people difficulty, and that include some of the pitfalls. Okay, so first things first. If you have the same base and you multiply exponents or indices, then you add the top. And this makes total sense because if you think about it, x to the second is x times x. X to the fourth is x times x times x times x. So you're multiplying x times itself 6 times, so that's equal to x to the 6. And by the same logic, y to the 7th, so anyway, if you divide exponents or with the same base, then you subtract the tops. So if you think about it, y to the 7th is y times y times y times y times y times y. That's 6 y's, one more. So we have y times itself 7 times. And then the bottom we have y times y times y. Well, these cancel out, right? So really it's just y to the 4th. Okay. When you don't have the same base multiple times, but if you take an exponent or an indice to another exponent or indice, that's when you multiply the tops. If we look at this problem here, if you have the same power, but different bases, you can factor out the power, as we see here. So you can multiply the bases, and then you can multiply the bases by one another and then take it to the indice or the power. And if you think about it, this makes sense because 2 to the 3rd is 8. 5 to the 3rd is 125. You multiply those together, you get 1,000. Well, 10 to the 3rd is also 1,000. Here's a common pitfall I want to show you. So it's interesting. This is xy times xy times xy. So a lot of times when people see this, they just distribute the 3 to both, right? X to the 3rd, y to the 3rd, and they say, perfect. And that works because if you write it out, it really is x times itself 3 times and y times itself 3 times. That said, that's not to be confused with x plus y to the 3rd equaling x to the 3rd plus y to the 3rd. This is not true. Because if you think about this one, by the same logic, this is x plus y times itself 3 times. Well, if you FOIL and then collect like terms on this, you're not going to get x to the 3rd, y to the 3rd. So if you see addition or subtraction, you can't distribute an exponent or indice across it. You can read about that. This is more of an SAT thing than an ACT thing on this part, but you can still read about that anyway. But what I want to look at is negative exponents because those come up quite often on the ACT. So if you have a negative exponent, all you do is it's just a base in the wrong place. So the negative exponent never stays negative. So on this one, 4 to the negative second, we just drop it and it's 1 over 4 to the second or 1/16. And I can show you why this is. If you think about it, 4 to the 3rd would be 4 times 4 times 4. So that's 4 to the 3rd. So if you think about it, then that's going to get us 64. 4 to the 2nd, 4 times 4, that's going to get us 16. 4 to the 1st is 4. 4 to the 0, hopefully you know this, anything to the 0 is 1, and we'll talk about why that is. 4 to the negative 1 is really just 1 over 4 to the 1st, which is 1/4. So if you look at this right column here, you should notice a pattern. And the pattern is every time your indice or exponent goes down by 1, you're multiplying by 1 less of your base. So you're effectively dividing by 4. That's why 4 to the 0 is 1, and that's why 4 to the negative 1 is 1/4, if you think about it. So anyway, that's a negative exponent. You just drop it to the base. If it's in the base, like it is here, a to the negative 5th, you just put it in the top. So no such thing as a negative exponent. It's just the base is in the wrong place. Okay, some common mistakes. So we know that a to the 3rd times a to the 2nd is a to the 5th. But you can't add these together. You can only add exponents together if you have the same base and the same top, the same indice. So this would be 4a to the 3rd. But in this case, we can't add them together. If you look right below here, root 5 is not the same as 3 minus 2. Right? Those are two different things. I can show you logically why that doesn't work. If you think about BIDMAS in order of operations, this is effectively 9 to the 1/2 minus 4 to the 1/2. Well, you can't subtract and then apply the indice or exponent, right? You have to apply the indice or the exponent first. So 3 minus 2, and then you subtract. So that's why those are different. Okay. Anyway, this mistake we talked about, this very common one, do not, and they'll try this on the test, do not distribute a power or indice or exponent across addition or subtraction. Okay. Let's talk about, this is a common type of problem. We'll do this one right here. There's a few of these on the packet. We're not going to look at them. But the way you do this example, and feel free to pause and try it if you want to. I know the steps are kind of right there. But you need to make sure you have the same base, and then you can compare the tops and figure out what k is. So if you think about this one, it's 2k plus 1 equals, if we want the same bases, 8 becomes 2 to the 3rd to the 4th. Well, 2 to the k plus 1 is equal to 2 to the 12th. So now that the bases are the same, if they're equal to one another, then the exponents have to be the same. So k plus 1 equals 12, k equals 11. So whenever they want you to try to figure out an exponent in the indice, a variable in the indice spot or exponent spot, make sure the bases are the same, and then you can compare the tops. All right, we'll keep it rolling. Let's look at how to do fractional exponents. So these are very important. It's very important to know how to do negative exponents, and it's very important to know how to do fractional exponents. Negative and fractional are key, and they're not that difficult once you get the hang of them. Negative and fractional. So I was kind of showing you fractional a second ago on one of the common pitfalls, but the way fractional works is the numerator is your power and the denominator is your root. So 7 to the 3/4 is really 7 to the 3rd root 4. If we look at this one below it, x to the negative 3/2. Well, first off, because it's negative, we're going to base in the wrong place. We just drop this to the denominator. So 1 over x to the 3/2. And if you think about it, that's really 1 over x to the 3rd root 2. Interestingly enough, though, even that's not actually completely simplified, because if you have 3 x's in here, whenever your numerator is greater than your denominator, you're not completely simplified if you try to put it in root form. And the reason why is if you think about it, we just need 2 x's, right? And then we satisfy the squared requirement. Like if you have the square root of 4, you know that's 2 because you just needed 2 2's to be able to take the 2 out from underneath the radical. So in this case, this is actually 1 over x root x, right? Because we can take out the x and then that 1x is left over. Anyway, and then a common thing you'll see is you'll see to the 1/2, Well, that's just to the first power, right? But then you just take the square root. So that's what that looks like right there. Anyway, big thing you'll see on the test is, or not big, but I'd say it comes up maybe once every 3 tests, is this idea of multiplying by the conjugate. If you multiply by the conjugate, it's how you rationalize a denominator. So how you make sure that you don't have a radical or a root in the denominator. So if we have this, multiplying by the conjugate would be multiplying by root 3, or actually in this case, we want to get rid of the root 3. Or no, it would be root 3 minus 5 over root 3 minus 5. So that's the same as multiplying by 1. And when you do that, what you get on the top is 7 root 3 minus 35. Sorry, I know it's a little tight there. And interestingly, root 3 times root 3 is 9. I'll do it out here actually. Root 3 times root 3 is 9. Root 3 times negative 5 is minus 5 root 3. Positive 5 times root 3 is plus 5 root 3. And 5 times negative 5 is minus 25. So what happens is these actually cancel out. You get rid of the root in the denominator, and it's just 9 minus 25. So this actually becomes 7 root 3 minus 35 over negative 16. So anyway. What did I do wrong? I'm saying minus 22 here. Oh, because root 3 times root 3 is not 9. You're probably screaming at the video. I am really sorry there. Root 3 times root 3 is 3. So 3 minus 25 is going to be negative 22. My apologies on that. So 7 root 3 minus 35 over negative 22. Okay, so scientific notation and then the 3 problems we talked about. So scientific notation is exactly what the title says it is. It's in science, we have really big numbers and really small numbers. We have things on a microscopic level and we have things on an astronomical level. And instead of having to write out really large numbers, we just use 10 to a certain power. So if you think about it, 10 to the power of 1, so if I have 8 times 10 to the power of 1, that's just going to be 8 times 10, or 80. So what happens is, if you have 8.0, whatever you're multiplying it by with the scientific notation, so if it's like 10 to the third, you just move the decimal spot over 3 places. So essentially, you're going to push the 8 over 3 places, and you're just going to have 3 zeros after the 8. 1, 2, 3. And so the decimal spot has moved over 1, 2, 3 places. So now you have 3 zeros. So 8 times 10 to the third is really just 8,000. And then here's another example here. Interestingly, if you have a really small number, if I have 3 times 10 to the negative 10, really this is 3 times 1 over, as you remember, no such thing as a negative exponent, just base in the wrong place. So 3 times 1 over 10 to the 10. Well, what that does is that just moves the decimal spot over the other way. So in this case, I'm going to move the 3, I'll move the decimal spot 10 places over. So we're actually going to have 9 zeros. 1, 2, 3. 1, 2, 3. 1, 2, 3. So by moving the decimal spot over, the first time I moved it over, the 3 goes right here, and then I go 9 more times, and that creates the 9 zeros. So it's all it tells you is how far to move the decimal spot to the right if it's to a positive exponent, or to the left if it's to a negative exponent. And hopefully take a moment to look over those, make sure those make sense. Okay, and as you already know, x to the 0, or any number to the 0 is 1, as we demonstrated earlier, and anything to the first power is just itself. Okay, let's look at these 3 problems. So this comes at the way end of the test, and I love this problem because it really hits on a very common pitfall. If you want, pause the video and try it out. The debate is usually between C or E. So see if you can figure out which one of those two is correct and why. But I'm going to keep on rolling if you haven't paused the video. So C is incorrect. Why? Because the mistake is to say, oh, it's 3 to the negative 100 plus x to the negative 100. Okay, negative exponents, drop the base. And to say, okay, it's C. And of course, they put C before E in case you take the bait on this one. But that's wrong. And the reason it's wrong is if you remember, we don't distribute across addition, right? X plus Y squared is not x squared plus y squared. Okay, so we don't distribute indices of cross addition. So because of that, it's not C. What we do though is we take this entire thing and we drop the 3 plus x to the base, and then we take it to the 100, positive 100, because we dropped it to the base. So the answer to this one is E. Okay, let's take a look at 20. 20 is a scientific notation one. So Walter recently vacationed in Paris. While there, he visited the Louvre, a famous art museum. Afterward, he took a 3.7-kilometer cab ride from the Louvre to the Eiffel Tower. A tour guide named Emily or whatever, sorry if I'm butchering the name, informed him that 2.5 million rivets were used to build the tower, which stands 320 meters tall. When written in scientific notation, the number of rivets used to build the Eiffel Tower is equal to which of the following expressions? So we just need to put 2.5 million in scientific notation. Okay, here's what's really interesting. You can get rid of D and E immediately because the rule with scientific notation is you only have one number to the left of the decimal spot. 2.5 million is 2,500,000. So what does that mean? That means that we need to essentially take this 2 and move the decimal spot over 6 places. So we need 6 numbers between the 2 and the decimal point, right? If you think about it. Here's the 2, and we have these 6 numbers between the 2 and the decimal point. So the answer is going to be A. 2.5 million is represented by 2.5 times 10 to the 6. Okay. So 22 is a problem I wanted to look at because 22 involves both understanding how to convert between fraction form and root form of an indice or exponent, which I said was important, and also negative exponents. And we also need to be good on order of operations. But the big thing is negative exponents and fractional exponents are something you want to have down, or root form. Okay, anyway. Pause the video if you want to give it a try. Otherwise, we're going to keep on rolling. So in this case, we can distribute the 4 because we're multiplying here. So this is 2 to the 4th, a to the negative 1 times 4, so to the negative 4. And then we have b to the 4 square root. And this is over a b to the negative 3. So let's do the negatives first. So we have 2 to the 4th. I'm going to write this as a fraction. So this is going to be b to the 4 over 2, right? Power over root. So 4 over 2 times to the 3rd, or times b to the 3. Sorry, not to the 3rd, times b to the 3. And then on the bottom, we have a to the 1st times a to the 4th. Okay, so immediately out front we get 16. That gets rid of a and b, right? We don't want 8. Then, in order to do this, because they have the same bases, we can add the tops. So we're going to call this 3. We're actually going to call it 6 over 2, right? So that's important. This is not 12. We can't multiply 4 over 2 and 3 over 2, we have to add the tops. So this becomes b to the 4 over 2 plus 6 over 2. And that gets us 10 over 2. So really, it's 16b to the 5th over And the bottom, a to the 5th. So we're looking at C there. Awesome. So hopefully that all makes sense. If it doesn't, feel free to review any parts of this video, and good luck on this worksheet.